Alright, so today's video is going to be about derivative tests, and that's going to be maximum and minimum values. So today we're going to do three things. We're going to find the intervals where the function is increasing and decreasing, find the local maximum and minimum values of the function, find the intervals of concavity, so where it's going concave up, where it's going concave down, and the inflection points. So, first off, the function we're going to be using is, so make that a bit neater, it's x to the power of 4 minus 2x squared plus 3. So, when we first picture this, we know that right away that this is going to be some sort of parabolic function it can break down to it. So, we'll keep that in mind for now. So, the first idea is we want to find increasing or decreasing. So, we want to find out where this is increasing and decreasing, so we must find the derivative of the function first. Alright, so let's do that. F prime of x, simple. We're going to take the power rule, 4x power cubed. It's going to become 4x plus 0. Okay. So, what we're going to do is, first off, is we're going to do the first derivative test to find out where we're going to have our intervals that are increasing and decreasing. So, when we're doing this, is we're going to have to make this whole thing equal to 0. So we're going to force this derivative to be equal to 0, and then we're going to solve for the value of x that would give at. So essentially we're finding our critical points. So in the form it's in right now, it's a little bit hard to see exactly what these points are going to be, so let's rewrite this in a form that is a little bit easier to see. Okay, so what this does is right off the get-go, we can see that when this is going to equal to 0, is going to be, well, when x is equal to 0. So that's one of our inflection points. Sorry, not inflection points, critical points. Got ahead of myself. So, in the other case, if you can see that if any time that either one of these are going to equal 0 is going to be when x is equal to plus or minus 1. So that looks like it's pretty much about it in terms of our critical points. So what we're going to do now is that we're going to apply the first derivative test. And so if you remember that if the derivative of the function was less than 0, then it was decreasing. And if it's greater than 0, then it's increasing. So if we check out our boundaries here, so we have 3 points, 3 critical points, and also by definition from previous videos, maximum values, it's when on either side of a critical point it changes from plus or minus, or it changes from minus to plus, and that's the function, by the way. So for x equal to negative 1, let's start off. When you plug that in, so any number between negative 1 and negative infinity are going to end up giving f prime of x to be, well, set less than 0 equals negative number. So that means it's going to be decreasing from negative infinity to negative 1. That's both equal to x, by the way. So now x equals to 0. Or, sorry, I shouldn't say when x equals 0. We're going on an interval here, so when x is from negative 1 to 0, what we're going to have is f of x is going to be positive. And so that means it's going to be increasing. And then once we have it at 0, and then we have our next critical point, is going to be plus 1, then f again is then decreasing. Now you can plug these in if you want to and check it all on the way, or just upon the pattern, it's essentially what has to happen in order for these to be critical points by definition. So, therefore, this is decreasing. And then from x equals 1 to positive infinity, it's positive. So it's increasing. Okay, so that's that part. And sorry this is going to be a bit long of a video because we have 2 more parts to do. So remember the second part of what I said we're going to do is find the local minimum and maximum values. So part B is going to be max min. Okay, so what we're going to do is recall our critical points. We're located at x equals -1, 0, and plus 1. So what we're going to do is we're going to plug back into the function and see which is the largest and which is the smallest. So to save time here, I'm just going to write these out, and I'll do the first one out here. So for -2, you're literally plugging in -1 back into the original function. That's going to give you 2. F of 0 equals 3. F of positive 1 equals 2. Now, and this is kind of what we expect because the form of our function could have been broken down into a quadratic. So that means that we have 2 minimum points somewhere along the way. So within our interval of a to b, you have a high point and minimum point. Be something like that. Might just be a straight parabola. Not exactly sure. I'm not going to graph it. So we do know that the points though are going to be between -1, 0, positive 1. And that's about all we know for right now. So we would have to expect local mins with the interval and one with the local max. So as before, as stated, at f equals 0 equals 3 is local max, and f equals plus or minus 1 equals 2 is the min. Alright, so that's going to bring us to part C. So finding the intervals of concavity and the inflection points. Okay, so in the previous video we described the concavity test. Concavity test is simply if the double derivative of x is greater than or less than 0, then the function is concave up or concave down. Okay, so recall that we had this for our first derivative, therefore that's going to be our double derivative. So, be easier to find if we factor out 12, leave with x squared minus 1 over 3. So, this is pretty easy to factor just like we did before. Every 12 up front, don't worry about that. You're going to have an x squared, so you know it's going to be x. And so this is going to be plus or minus 1. Kind of treat it like a 1, but it's pretty easy to see that these are just going to be your factors. So you can multiply that back together and check if you like. And then, therefore, when x is greater than 0, that's going to happen when x is greater than 1 over the cubed, or square root of 3. or when x is less than negative 1 over square root of 3. So what this means is that our double derivative of x is greater than 0 on an interval from negative infinity to negative 1 over square root of 3, and then again from 1 over square root of 3 to positive infinity. And then what happens is that you can see that for it being negative is going to be simply when x is between those two values. So f of x is concave upward for prime being positive, so that's going to be this case, and it's going to be concave down for prime negative, which is the case we had right below. So now to define the inflection points, we're going to have to determine where the function changes from increasing to decreasing. So we know the points are going to be at x equal to plus or minus 1 over square root of 3, we'll change that back to black, and we need to find the values of the x. So when x is equal to plus or minus 1 over 3, to find out where those values in the actual function are. So what this is going to equal is going to be plus or minus 1 over root 3 that's going to be e to the power 4 minus 2 times plus or minus 1 over root 3 minus 2 plus 3. And what this simplifies out to be is 22 over 9. So the inflection point is actually at plus or minus 1 over root 3 and 22 and 9.